AP Calculus BC, Unit 6, Day 2, Office Hours. This was the assignment. So some more slope field practice. Okay. So it says match the slope fields with their differential equations, then solve the differential equations for 1 through 3 because you can't on 4, and for the initial condition. I also want you to sketch the particular solution on your slope field. I mean, that's what you're trying to do. Well, you're trying to match it, but then you could sketch it. So what I would look for is just basic, easy to identify things like 0. When's this equal to 0? Well, that's going to be when x equals -2. So we're looking for one that has a bunch of 0 slopes along a vertical line, x equals -2, which seems to be clearly B, right? I mean, you can look for other things, positive slopes, negative slopes, but I think that narrowed it down. This one equals 0 when y equals 0, which is going to be the x-axis only. So that looks like D. This one equals 0 is going to be when x equals 0, which is the y-axis, 0. So I think that alone is A. You could look for undefined, which is going to be when y equals 0, which is the x-axis. So it should look like it's going vertical on the x-axis, which, let's see. Okay, x equals 0 along the y-axis. So that's A. Along the x-axis, it looks like it's going vertical, right? So next one equals 0 is going to be y equals x. So along a slanted line, that. So I think that's C. So just by process of elimination, we could go further. We could look at positive slopes, negative slopes, just if there's any two that it's hard to tell. Now, sketching the specific solution, 0, 2 would be right here, and it would be like this. Now, here's the deal. You might be tempted to do the whole circle, but it's only going to be the top half because, one, it's a function, and it would violate that. It's the top because it goes through the initial condition. But also, right here on the edges, this derivative for A is undefined. So you got to split up the domain is only includes where the initial condition lies in any points where this is undefined, which is at y equals 0, or the solution's undefined, then you got to split it up there. So I'll come back to those in a second. So 0, 2 here would be like that. 0, 2. And I think this is fine. So we put arrows on the ends here because it's going to keep going. So you either put solid dots at the end, or put arrows, and it keeps going. So probably something like that. 0, 2 here. So when you do this, I want you to label that initial condition very clearly. This is a slant asymptote. And 0, 2 here. This kind of looks like a exponential. We'll see. So those are sketches. Now let's solve these. Separate the variables. This one's pretty much already separated because it only has x's. So we've been undoing derivatives, for a long time, and they just have x. So that's going to be y equals 1/2 x squared over 2 plus x plus c. Now let's find the c value because we have the initial condition here. It's better to find it right away. So 2 in for y, 0 in for x. So c equals 2. So y equals 1/4 x squared plus x plus 2 is the solution. And remember, that was B. It looks like a bunch of parabolas, so that makes sense. The domain, which is required with the solutions of differential equations. Are there any issues here? Nope. Are there any issues with the derivative being undefined for any x or y values? Nope. So the domain is everything. But that should be part of your answer. Okay, next one. We have to separate the variables, then integrate both sides. Okay, find the c value now. Plug 2 in, 0 in for x. So c equals natural log of 2. So natural log of the absolute value of y equals x plus natural log of 2. And then we can exponentiate both sides and then get rid of the absolute values and be plus or minus. Now, rules of exponents I'm using to break this up. I usually don't write it. I do it in my head. But that's going to give you 2 in front. Now, you need to decide if it's the plus or the minus now with the initial condition. If you plug in 0, you should get positive 2. So it's got to be the positive. So that's your equation now. Are there any issues here with any domain issues here? Nope. Any domain issues with the derivative being undefined? Nope. So it's going to have a domain of all reals. On the AP test for response, that's a requirement with your answers. So I want you to just get in practice doing it every time right now. Because it's one of the hard things. People forget to do it. So one of you do it all the time, you'll less likely forget. And then also people, these ones are pretty easy, but we're gonna see some more challenging ones. This one, separate the variables. So it's gonna be y dy equals negative x dx. I'd leave the negative on the right side. It's gonna be y squared over 2 equals negative x squared over 2 plus c. You can find the c value now. So we plug 2 in for y, 0 in for x. And it should come out to, okay. So then c equals 2. So we have y squared over 2 equals negative x squared over 2 plus 2. Now, we could keep going and solve for y, which is actually what you should do. Even though, by the way, this looks like the equation of a circle, right? Which, remember, A looks like a circle. But you're expected to solve for y. So it's going to be plus or minus. I multiply both sides by 2. And then I take the square root of both sides. So it's going to be negative x squared plus 4. You got to decide is plus or minus. If you plug the initial condition in x equals 0, and you should get positive 2. So it's going to be the positive. Now the domain, this right here, the inside of this has to be greater than or equal to 0. So that's an issue right there. And you could do x squared minus 4 is less than or equal to 0. And usually a line check is helpful here. Well, actually, you know what? I'm not even going to do a line check because if I want to find the actual domain, it's actually more work. But we know it's simply just a number line where you put negative 2 and 2 on there. Also, by the way, y equals 0 is an issue in the derivative. So you got to make sure that y cannot equal 0, which is what we just found. Right? And so if you're to solve this, you're going to get the same thing that we just got right here, plus or minus 2. So you have to put these as open dots. Even like right here, it's okay. Here, it's not because it's going to cause division by 0. But even if it seemed okay everywhere, you're going to put open dot. It's a single open interval, and then identify. You got to get everything in terms of x. So even though y can be 0, you can't put that on the x number line. So you got to get the x values that make y to 0. And then we don't need to do any tests or anything like that. It's easier. You just identify the initial condition was x equals 0. So it's this chunk. It's either this chunk or this chunk or this chunk. Single open interval. So this would be for the domain negative 2 to 2. So that's a requirement, okay, to be a part of your solution. Now, number 4, I told you not to because we can't separate the variables. So don't worry about it. Okay? Now, these all make sense. This looks like the top half of a circle. This looks like an exponential, right? A positive exponential. This looks like a parabola opening upwards. So the solution should totally make sense. Okay, number 5. The calculator drawn slope field for the differential equation dy dx equals x. Y is shown in the figure above. The solution curve passing the point 0, 1 is shown. So they drew it in there for you. Okay, cool. Sketch solution curve through 0, 2. Well, that would just look like this. And we should put arrows on the ends, indicating it keeps going. Sometimes they stop if there's a domain issue. Solution curve through 0, negative 1. Okay. And then let's see. Solve the differential equation for 0, 2. Okay, so we need to separate the variables. Integrate both sides. Plus c. Find the c value. So you have an xy pair. Plug those in. Rewrite it. Exponentiate both sides, which I would use rules of exponents to break up the exponent, because then that's just going to give you a 2. Take the get rid of the absolute value by doing plus or minus. Decide if it's the positive or negative. Now, if you plug in x equals 0, you better get positive, so it's going to be the positive. And then, and so these graphs look almost like parabolas, but they're actually exponentials, but they have an x squared in the top. So even when you plug in a negative, that it gives you the symmetry, like the left half looks the same as the right half. The domain, are there any issues here with the domain? Nope. Domain there? Nope. So we'd say for the domain, this works for the domain of negative infinity, positive infinity. So it kind of looks like an exponential, but then the left side is just like the right. It's almost like a reflection. And so it looks like this. It seems like there could almost be an issue right here where you get like a corner or something where the derivative is undefined, but I guess it's really smooth. It works out really nicely. So it's kind of what's going on. Okay, calculation drawn slope field for differential equation, which we can't solve we can't separate the variables, but we've seen this several times. This is what the slope field looks like, no surprise. 0, 1 is right here. So it kind of goes like that. Negative 3, 0. Be like that. So it's kind of weird, like get totally different solutions. This is the one, by the way, that does have the specific or the general solution like this. So we could find the specific solutions if you just memorize this, So like if you were to plug in 0, 1, this is just interesting. See, this is general solution for both of these curves, even though the curves look totally different. So let's see how that works out. So it's going to be c equals 2, right? So it's going to be y equals 2 e to the x minus 1. So that's for part A. That's its general solution. And Domain should be all reals. This one would be you plug 0 in for y. So that's going to be positive 3. That's going to be c e the negative 3 equals negative 2 divided by c. Oh, wait, no, we're trying to solve for c. So divided by e to the negative 3. So we get negative 2 e to the 3. So that's what c is. So when you plug it back in, you get negative 2 e to the 3 e to the x minus 1. So you get negative 2 e to the x plus 3 minus x minus 1. So that's the solution for this one. So it kind of gives it a different shape. It's upside down, it's negative. You have this extra term inside that shifts it. So kind of interesting. Anyways, okay. On the back, these are a little different. So these say to match the slope field with the equation that slope field represents. So this is actually, the equation, not the differential equation. So we're not trying to match them to the derivatives, the actual functions. So that should make this a lot easier. Like we're looking for a graph that has a bunch of horizontal lines in it, right? Well, that'd be D, right? We're looking for a graph that has y equals x lines, so that'd be H. We're looking for a bunch of parabolas. Well, that would be, that looks like C. This is a cubic, or are there a bunch of cubics? Maybe F. F looks the closest to a cubic. Right? That's what a cubic looks like. A bunch of parabolas, a bunch of lines. Right? This one is rational function, has vertical asymptote, horizontal asymptote. It's always positive, so it looks like that. So that looks like, I think, A. This one is just a sine curve. We're looking for something that looks like a bunch of sine curves up and down. So I would say E. Cosine curves. I like sine curves. That'd be B. Natural log of x looks like this. And then usually it's not defined over here, but if it has the absolute value, the right half gets copied on the left half. So that looks like G. Anyways, usually they're not that easy, but I threw you some easy ones. So here's a good good like free response style question. Differential equation. X can't be 0 because it's division by 0. It says on the axis sketch slope field given for 8 points. You'll notice that there are no points here, here, and here. And the reason is the slope is actually undefined. And I know that sometimes I'll sketch a vertical tangent line, but technically you're not supposed to do that. It doesn't exist. It's like a vertical asymptote on the graph. So the graph can't exist. So, when is this equal 0? When y equals -1. Okay. When is it undefined? Well, we already said that we can't sketch those. We could plug 0, 1 in. 0 for x, 1 for y would be a slope of 2. And there might be like symmetry across this, right? -1 for x, 0 for y would be 1 for x, 0 for y. That should actually be a slope of 1. And this would be -1. And then 2 for x, that'd be 1/2. So 1 over 2. And this would be -1/2. And then 1, 1 would be a slope of 2. And -1, 1 would be a slope of -2. And 1, 2, 3, 4, 5, 6, 7, 8 points. Not less, not more. Okay. So it's find the particular solution, y equals fx, to the differential equation with the initial condition and state its domain. Even if they don't tell you to. They used to like say it, but now it's just a given. Okay? So let's see if we can solve the differential equation. Got to separate the variables. Integrate both sides. I'd find the c value now. So your x, your y. So it's going to be natural log of 2, natural log of absolute value -1, which is natural log of 1, which is 0. So c equals natural log of 2. Exponentiate both sides. Rules of exponents say this could be e to the natural log of x times e to the natural log of 2, which is going to work out really nice. Then to get rid of the absolute values, you got to do plus or minus. So this is going to give you a 2, and this is going to give you absolute value of x. Then we subtract 1 from both sides. Now, we should also decide if it's positive or negative right now. If you plug in -1, you should get positive 1 out. So you plug in -1, plug in -1. That gives you 2, and you get positive 1 out. That gives you 2. It needs to be positive. Now, this isn't on any of these solutions of differential equations. If it involves absolute value, that is for sure a place where you're going to have to break it up because absolute values have corners where the derivative isn't defined, and that's something that for sure would cause you to break it up. So the original derivative. Now, there are no domain issues here. That's all reals. But up here, x can't be 0 because then the derivative is undefined. And since this came from that, we can't say this exists where that didn't exist, right? And so usually we just do a number line and we put 0 on there and we say, okay, well, is it this piece or this piece? It's only one of them, single open interval. We don't just eliminate that point. We eliminate everything other than the single section where the initial condition is. So this is a picture of your domain. So the domain is going to be negative infinity to 0. Now that needs to be in your answer, but that also has some effects here. That we're only going to plug negatives in, right? So if you're only going to plug negatives in, then you know that this is going to be negative, and you can simplify it by getting rid of the absolute value and adding an extra negative to force that thing to happen. You're only going to put negatives in here, which means you're going to get the opposite of it. And so if you put negative in x, now it's for sure going to be positive. This extra negative is going to force it to be positive if you know you're plugging negatives in. So this is your best solution. And that's what you need to write. So because of the domain restriction, we actually end up being able to isolate it to a specific line. Now going back, we just drew a picture of this graph. So -1, 1 is right here. And sometimes they would ask you to sketch this. They didn't this time, but I'm going to do it anyways. So it's going to look like, actually that was supposed to be a slope of 2, right? So it's going to look, if you're to follow the slope field, you get this V graph, which makes sense with an absolute value. But because the slope is undefined there, remember, we didn't even graph it. Okay, so I would have been tempted to put a vertical line, but it's not even a vertical asymptote this time. It's actually a corner. So the solution would only be this part of the graph, the left half, because that's the initial condition. It's either the left or the right. And if it's just the left half, that's just the equation of a line. So that's why it makes sense. Now, I think I should jump back to a problem I did in the front. On this first one, A, these should be open dots because the domain should not include, should be a single open interval. Okay, so that's it. Okay.